So now that we have talked about the two mechanisms, and we have mentioned, okay, what are some of the things we need to look out for? If you give me data, I roughly figure out, okay, based on the data, I can decide whether this is SN1 or SN2. But sometimes if they never give us data, we still can decide whether this is SN1 or SN2 mechanism, because the nature of your halogenoalkane, whether this is primary, secondary, tertiary, actually has an influence over whether it favors SN1 or SN2. So let us try to talk about this here under the types of halide. Now we have this list here involving the different halides. This is a methyl halide, that means no R group, primary halide with one R group, secondary halide, tertiary halide with 3 R groups. This is my phenylmethyl halide. So technically speaking, if I try to categorize this, this is a primary halide. But this actually will favor SN1 mechanism. So we will talk about it along the way. In terms of the mechanism that it favors, these two guys, methyl halide and primary halide, will tend to favor SN2. Tertiary halide will favor SN1. Phenylmethyl halide, if there's a benzene involved, it will favor SN1. Secondary halide depends, because secondary halide is like somewhere in the middle. So the question will have to give us data for me to decide whether it favors SN1 or SN2. Of course, once we have this trend, we want to understand why this is the case. How come certain species will favor SN2, certain species will favor SN1? So what we want to discuss is the 3 effects, steric effect, electronic effect, resonance effect. And a combination of these 3 ideas, interestingly, can explain the reactivity of all the function groups that we have in syllabus. So we want to have a rough idea what each of these effects mean. So let's run through each one of them part by part. Okay, the first one is involving my steric effect. Now, steric effect, maybe let me focus on this portion here so that we will not be distracted by the resonance effect. So if I focus on this portion here, all right. Now, you notice the steric effect is linked to the number of bulky R groups that is attached to my reactive carbon. The idea of steric effect is pretty simple. If I'm attached to a reactive carbon or reactive species, then I'll take up a certain space around the reactive species. Then I'll act as a barrier, physical barrier, to block the entry of my incoming group. Just by being there, I just take up certain space around the reactive species. Then I can block the incoming group. And I can reduce the reactivity for the reactive species. Of course, how good I am in terms of blocking, it depends on how big my size is, correct? The bigger I am, I can take up more space around the reactive species. Then I can act as a more effective shield to block the entry of my incoming group. So basically, that's the idea of steric effect. Now, steric effect, we use it to target SN2 mechanism, because SN2 mechanism, it is the backdoor attack. So when the OH minus comes in through the backdoor, you notice the 3 groups are pointing towards the incoming group, the nucleophile. So therefore, they will act as a barrier to block the entry of your incoming group. So how effective they are in terms of blocking the OH minus, of course, it depends on the size. If I look at my methyl halide, this is hydrogen. Hydrogen is useless, right? Because hydrogen is like peanut size. It has only 1 electron, which is involved in the CH bond formation. So basically, it doesn't have any spare electron cloud to act as any effective barrier. So the OH minus can just walk in and kick out the X minus. Basically, the back door is like super exposed. There's nothing to block the entry of your incoming group. And if you're a methyl halide, you will favor SN2 mechanism. If you're a primary halide, you also favor SN2 for the same reason, because there's only 1 defender. There's only 1 guy to block the entry of your incoming group, which is basically doesn't really block much. OH minus can walk in and kick out the X minus. So if you don't have a lot of R groups, you favor SN2. But if you have a lot of R groups, let's say 3 R groups, then basically the R group will take up a significant portion of space around this carbon. You block up the back door, and it makes it very hard for the OH minus to come in. And OH minus, if you cannot attack from directly behind the CX bond, then you disfavor SN2 mechanism. Of course, if you disfavor SN2 mechanism, it doesn't matter. You can always go by another way. You can go by SN1, correct? So if it doesn't go by SN2, I can always go by SN1. But the idea involving steric effect is this: the bigger the size, the bulkier it is, the greater the steric hindrance. Steric hindrance is just a technical term for me to say that It acts as a physical barrier to block the entry of your incoming group. I just stand down there and just take up a space around the reactive species. I make it harder for the incoming group to come and attack the reactive species. Just like if you play sports, if you are a defender, you always block yourself. You place yourself between the attacker and the goalpost. Just by being there, you make it harder for the attacker to go and attack the goalpost. So the idea is effectively the same. Just by being there, you act as a barrier to block the entry of your incoming group. So the idea, basically, it is the steric hindrance. Also, the bigger the R group, the bigger the R group, or the more these bulky R groups we have, the greater the hindrance, harder backdoor attack. So therefore, you disfavor SN2. So stereo effect says that if you have more R group, you will disfavor SN2, then you go by SN1. If you have less R group, then you favor the backdoor attack, then you go by SN2. Stereo effect is saying that this outcome, correct? Now the next effect that we want to talk about, it is the electronic effect. Electronic effect is based on something that we are more familiar with, donating withdrawing groups. Donating groups will push electron, obviously, to anything that it is attached to. Withdrawing groups will pull electrons away from any group that it is attached to. Now, how the electronic effect affects the stability of my carbocation, because electronic effect is used to explain SN1 mechanism. SN1 mechanism is involving the formation of your carbocation. So therefore, the focus is on the stability of the C+. The more stable the carbocation, the more likely it will be formed. So therefore, it will favor SN1 mechanism. And we know that R group is electron donating, correct? So the R group is capable of stabilizing the C+. But before we understand that, we have to understand the rationale involving if you are a charged species. If you want to be stable, then we want the charge to be as neutral as possible. Let's say, for example, if I'm positively charged, I'm a carbocation, I'm positively charged. If I want to be stable, then I want to be as neutral as possible. Because if I'm positively charged, I'll attract negative things. If I'm negatively charged, I'll attract positive things. If I'm neutral, then nobody will come and disturb me, right? Nobody likes me if I'm neutral. So that's the best. So if I'm positively charged and I want to be stable, then what I like is I like things that can give me electrons, make me less positive or make me more neutral, then it'll make me more stable. So we have to understand the rationale involving, in terms of the charged species, what makes that guy more stable, what makes that guy less stable. So if we want to make it more stable, the magnitude of the charge will be, we want it to be as small as possible, or we want it to be as neutral as possible. So positive species will be stabilized by donating groups. So R groups, which is electron donating, push electron to your C+, make it less positive. So therefore, this is stabilizing. And of course, the more R groups we have, the more stable it will be, correct? And if I consider these two guys, if I have more R group, C+ will be more stable, it will be more likely formed. So therefore, it will favor the formation of my carbocation. In turn, it will favor SN1 mechanism. Now, compared to this guy, methyl halide, this is the carbocation that we will be forming, not stabilized by anything. So this guy will be relatively less stable. You will disfavor the formation of your carbocation, which means that you disfavor SN1 mechanism. Disfavor SN1 mechanism doesn't matter. It just means that you can go by the other way. If disfavor SN1, then you go by SN2. If you favor SN1 mechanism, if the carbocation is stable, favor SN1 mechanism, then you go by SN1. So both electronic effect and stereo effect, they have the same outcome. Stereo effect and electronic effect both says that if you don't have R group, you go by SN2. If you have a lot of R groups, if you have 3 R groups, then you go by SN1. That means they are in agreement with each other. So eventually, most of the time when we do explaining mechanisms or reactivity of other functional groups, we will be using electronic effect more often, the idea involving donating groups and withdrawing groups. Now remember, electronic effect, donating, withdrawing groups, the idea is if I'm attached to you, depending on whether I'm donating or withdrawing, I will give you electrons or I'll take electrons away from you. I will change your charge. In turn, I'll affect your stability or reactivity. Stereo effect is I'm attached to you. I take up some space around you, make it harder for an incoming group to come and disturb you. So these two effects actually, in terms of nature, they are a bit different. So we want to be able to differentiate these two guys. Now, how about the resonance effect. Now, coming back to this guy here, you notice what we have for our phenylmethyl halide. In terms of categorizing it, this one's supposed to be a primary halide, but it still favors SN1 mechanism. The reason is because of the stability of the carbocation ion. So let me just show you here. We can take note of this guy. Now, the intermediate form, if you draw out the intermediate, it'll be something like this. The positive charge is next to benzene. And if I have a positive species next to benzene, then it can be stabilized by resonance. And resonance stability is a big deal. We will talk about it along the way. Now, the idea is, how can this C plus be stabilized by resonance? Because benzene has this delocalized pi system, correct? And C plus doesn't have any electrons, but it has an empty pz orbital. So it has the space for the electrons from benzene to be delocalized into my C plus. So effectively what is happening is the delocalized pi system in benzene will overlap with the empty pz orbital. So the electrons in benzene can go to your C plus, and now the delocalization is extended to your C plus. So therefore your carbocation is also stabilized by resonance. As long as you have this delocalization, you have this delocalized pi system above my carbon, the guy will be protected or being sheltered by resonance. So benzene has this delocalized pi system overhead, stabilized by resonance. And if it can delocalize to my C plus, carbocation ion, the delocalization is extended to this C plus. This C plus is also protected by resonance, stabilized by resonance. And if the carbocation ion is stabilized by resonance, then it will favor SN1 mechanism. I think in terms of appreciation, we want to understand that resonance effect in terms of the stabilizing effect is a lot more significant as compared to the electronic effect, normal donating withdrawing groups. Because if I compare what we have here involving this particular trend, if I want to decide whether a normal halide, whether this is a primary, secondary, or tertiary halide, whether it favors SN1 or SN2, if it is a primary halide, if it is only attached to one R group, actually it will favor SN2 mechanism. Only when you have a tertiary halide, when your halogenoalkane is attached to 3R group, then the carbocation ion is stable enough for it to favor SN1 mechanism. And if I compare this with benzene, I only need one benzene to stabilize the carbocation ion in order for it to favor SN1. So we want to have this appreciation. My electronic effect is actually a lot more stabilizing as compared to electronic effect, normal donating and withdrawing groups, because if we consider the stability of my carbocation ion and favoring SN1 mechanism, I will actually need a total of 3R groups to stabilize the C plus enough for it to favor SN1 mechanism. If it is 2R groups, we actually don't know whether this is SN1 or SN2. If it is 1R group, it will be most likely SN2 mechanism. But I only need one benzene to stabilize the carbocation ion to the same extent. So very roughly, it would suggest that the stabilizing effect of one benzene is equivalent to 3R groups. So we want to have this idea, this appreciation that resonance effect is a lot more significant as compared to the normal donating withdrawing groups effect, the electronic effect. So you keep this idea in mind. And for this reason, and another reason that we will talk about under additional notes, for this reason, we want to separate benzene. We don't try to categorize benzene as electron donating or electron withdrawing, because maybe at the beginning, some of us might be wondering, hey, benzene, is it donating or withdrawing? My preference is benzene is different. Benzene will stabilize species by resonance and to a much more significant extent. So we don't categorize benzene as electronic effect, normal donating withdrawing groups. Okay? So I think it's good to keep this in mind. Now, as mentioned, a combination of these three guys, along the way we will have a lot of reinforcement. A combination of my steric effect, electronic effect, and resonance effect will explain the reactivity of all the function groups in syllabus, believe it or not. And we will get to reinforce this along the way. And usually it is either involving electronic effect, donating withdrawing groups, and resonance effect. As long as it is attached to benzene and there's delocalized pi system, there's resonance effect. Electronic effects, donating withdrawing group effect. Most of the time, we will use a combination of electronic and resonance to explain reactivity. On and off, we might make use of steric effect. Steric effect, remember, is if I'm attached to you, I'll take up some space around you and make it harder for the incoming group to come and disturb you. That idea physical barrier idea, this is the steric effect. But these three effects are very fundamental, involving explaining the reactivity of all the function groups in syllabus that we will encounter. So you do keep this in mind. We will talk about this along the way. Now, I've mentioned that the reason why I don't like to categorize benzene as a normal donating withdrawing group is because resonance effect is a lot more stabilizing than normal electron donating and withdrawing groups. Now, there's another reason why we want to categorize it differently is because if I look at electronic and resonance effect, the way it stabilizes species is very different, because a normal donating and withdrawing group cannot stabilize all species. It can only stabilize either positive or negative species, and it cannot stabilize everything. But benzene can stabilize any charge that it is attached to, which is which in my opinion is also something very interesting for benzene, that normal donating groups and withdrawing groups are not capable of doing. So we want to again have this appreciation. So if I use electron donating group as an example, a donating group will push electron to anything that it is attached to. So depending on the charge of the guy, you will either stabilize it or destabilize it. So if I am positive charge, if I talk about carbocation, you notice donating group will push electron to a C+, make this C+ less positive. So therefore, this is stabilizing. Remember, if I am charged, if I want to be stable, I don't want to be positive charge. I want things to give me electron, make me less positive. So therefore, make me more neutral. That's stabilizing. So if R group give me electron, less positive, this is stabilizing. So my electron donating R group can stabilize positive species. But the same electron donating R group, if it is attached to negative species, O-, for example, you notice it will become destabilizing, because if I'm negatively charged, if I want to be stable, I don't want to be negative. I want to be neutral. So I want things that can help to take electrons away from me, but this electron donating R group still give me more electrons, which means what? Which means that I will become even more negatively charged, and this will be destabilizing. You notice the same electron donating R group will stabilize positive species, it will destabilize negative species, depending on the charge that it is attached to. Of course, withdrawing group will be the other way around. Withdrawing groups will destabilize positive species, will stabilize negative species, but the idea is a normal donating and withdrawing group cannot stabilize all the charges that it is attached to. Now, if you find this familiar, actually this explains why alcohols are less acidic than water. We say that electron donating R group will intensify the negative charge on oxygen, so conjugate base for your alcohol will be less stable. So therefore, alcohol is less acidic than water. If we talk about intensify negative charge on oxygen, maybe it will trigger some memory. Maybe we can remember that. This one is explaining the acidity of alcohol versus water, why alcohols are less acidic than water. So you notice acidity is explained under electronic effect, involving donating and withdrawing groups. Now benzene, let's look at benzene on the other hand. Benzene is interesting. It can stabilize anything that it is attached to. It can stabilize positive charge, which we have talked about earlier, because basically what the benzene is doing is, if you're positively charged, my electrons will delocalize into your positive charge, then we'll share the positive charge. We'll spread out the positive charge, share amongst many carbon or a bigger region, and then you stabilize this C+. And if it is a negative charge, let's say O-, it is also capable of stabilizing this O-. If you're negatively charged, your electrons can be delocalized into my pi system, and we share the negative charge over a bigger region, and same thing, you'll be able to stabilize this negative charge. So you notice in terms of how the electrons are moving is, if carbon is short of electron, delocalized pi system will go to C+, push electron to C+, make this C+ less positive, stabilize the C+. If this is O-, how the electron is being is moving is the electrons will move from O-, delocalized into benzene, and the negative charge is moving away from oxygen into benzene. So this O- will be less negative. Again, this will be stabilizing. And you notice this one is the conjugate base of phenol, explaining why phenol is more acidic than water, because negative charge on your O- can interact with benzene. So therefore, this guy is stabilized by resonance. Consequence is your phenol is more acidic than water. So benzene is interesting. Benzene can stabilize both positive species as well as negative species, which makes it quite different from normal donating and withdrawing groups. Again, what we want to emphasize here is we want to have this appreciation that benzene is a bit different from the rest of normal donating withdrawing groups because it can stabilize any charge that it is attached to, and it can stabilize species to a much more significant extent. So therefore, when we subsequently encounter things involving benzene, then we will be more mindful involving benzene. We will give species directly attached to benzene a little bit more attention. We want to have that awareness. We want to have that awareness. And along the way, we will have more reinforcement because in my opinion, I think this idea is important. Ken? But basically, this is the overview involving nucleophilic substitution mechanism.